Assalamu alaikum. This is Bashar Al-Hais with my friend Aman Izhar. We are from KFUPM, and this is our research presentation for Abu Dhabi undergraduate research competition. Our research is about speech and motion recognition. Feelings play an important role to comprehend a conversation. So with better understanding of feelings, of the communicator feelings, we can have better responses. Therefore, human-computer interaction can be improved with better analysis of emotions, and speech is one of the modalities in which we express emotions. So our problem definition, our objective in this research were to analyze convolution neural networks and see the effect of feature fusion at different level with the same architect blocks. And we measured the effect of it on different matrices, such as memory space and accuracy. So the past research that were done in this field, the audio features that were studied were time domain features, which include pitch frequency and short time zero crossing rate, also frequency domain features and statistical features. And the meaning of feature fusion is that we render a new feature from combining several other features. So the models that were used in past research included support vector machine, which were applied in UMO database, and they showed high accuracies. Also convolutional neural networks. They rendered good results on Tedlium2 datasets, and generative adversarial networks. They were also applied to augment the performance of SVM. So how CNN work in general in our research, we have an audio image, and then we apply filters through it to extract the features, and then we pass it to a fully connected layer in which we have a softmax activation function that will classify the audio feature. And our research included 4 different data sets with the total number of files were 11,318, and we split 77% for training and 23% for validation. And the bar chart represents the number of files for each class, which include angry, happy, and sad, and so on. Now I'll leave you with my friend Aman, who will continue the presentation.
Thank you, Bashar. Now I will elaborate on the methodology that we use in our experiment. It is the steps are basically 4. The first step is the feature extraction, which is extracting audio features. The second one is building a machine learning model. The third step, we construct 5 CNN models where we fuse the features that are coming out of the CNN models at varying levels. And lastly, we compare all these models in terms of accuracy and the memory space that they occupy. Here is a list of all the hardware and the software setup that we have used. We used an NVIDIA graphics card, which the model was RTX 2060 Max-Q. Our machine held 16 GB of RAM, and it was a 64-bit machine. For the software, we used Python for basic programming, and then TensorFlow and Keras for building our deep learning models. We used Librosa for extracting the audio features, and scikit-learn for building ML model and for pre-processing the features. The first step, which is extracting the audio features, consisted of extracting 3 audio features that gives meaning to any audio in the wave format. The first feature was the MEL spectrogram, which is a power spectrum of a sound. The second one were the MEL frequency cepstral coefficients, which are called as MFCCs. They usually describe the overall shape of the spectral envelope. Typically, we extract 10 to 20, and in our experiment we extracted between 10 to 13, as they give or describe the most out of any audio file. The third one is a chromogram, which is just a transformation of time frequency versus the pitch. In our first model, we basically employed a machine learning model called the voting classifier model. It consisted of 3 mini models. The first one was the SVM, or support vector machine. The second one is the logistic regression model, and the third one was the random forest model. In all these 3 models, we first extracted the features and then applied principal component analysis, reducing or decomposing them into 200 components, and then feeding it to all these 3 mini models. And after each of these mini models are done with the labeling or classifying the emotions, the voting classifier would classify them based on majority voting, and that will be our real label. With respect to the deep learning model, I'll first describe our model 1, where the feature fusion is taking place at the feature extraction level. For this, we built a convolutional, we built the same block of layers. We use the same block of layers in all the 5 models, and the block of layers consists of its basic CNN layers, followed by batch normalization, followed by max pooling, and then a dropout. So in model 1, we take all these 3 features represented as matrices, and then we extract features by passing it to these blocks of CNN blocks. The resulting matrices are then concatenated at the feature level and then passed to the dense layer. After the dense layer, it is passed through the softmax layer for classifying the emotion. Hence, we are calling it feature extraction at the feature level. Then the CNN model 2, here we fuse the model at the output level, which is similar to the first model that we described. However, the fusion here takes place after passing it through after passing the features through 3 individual dense layers. Hence, they are concatenated or fused at the output level, and then they are classified using a softmax function. The third CNN model, we fuse the features at multiple levels. So here at first we fuse MFCCs and chromogram at level 1, and then whatever feature we are getting, we concatenate it with the MEL spectrogram feature, concatenating them at level 2. And then we feed forward them to a dense layer followed by softmax, and then we classify all the 6 emotions. With the CNN model 4, we fuse the features at the input level. However, we change the orientation. We stack them horizontally. So at the end, at this horizontal level, the matrix the feature matrix is of the form of 13 cross 924. So 924 are the features that are horizontally stacked. And then we pass it to our CNN block, followed by a dense layer and a softmax function. Lastly, in our 5th CNN model, we fuse these features at the input level only. However, the orientation is vertically, which means that all these features, when concatenated at the input level and vertically stacked, they give the matrix of the shape 39 into 308. So at this vertical level, they are concatenated, or you can say stacked. And the rest of the model is pretty much same as the model 4, which consists of one CNN block or this layer, and then followed by a dense layer, followed by a softmax function. Moving on to the results and the evaluation. The whole experiment was to analyze or see what actually happens when features are fused at varying levels using the same blocks of neural networks. And this study highlights many important results. First of all, with respect to the memory space that the model occupies, we observed that model 5, where feature fusion takes place at the input level but vertically stacked, it takes the lesser memory, which is only 5.3 MB per model. And this model 5 itself, it beats all other model in terms of accuracy, precision, recall, and F1 score. Here we present the training curves of the model 5, which was our best model. In conclusion, we have analyzed how the behavior of fusing the audio features at different level plays a critical role in determining the performance of the model. And the performance with our experiment were with respect to the accuracy and the memory space occupied. And we observed that model 5, where feature fusion takes place at the input level and all the features are extracted vertically, it gives the highest accuracy and displays the best performance, occupying only 5.3 MB of memory space. Therefore, we presented a study where developing neural networks for speech emotion recognition works well when audio features are fused at the input level and CNNs are used for feature extraction. This also implies that if we add more features to it, it could give a boost in the performance. As for our future work, we have observed that if we can improve, not only we can add more features, but also we can improve the model or the block of CNN layers furthermore to extract more rich features out of the input, out of the input, so that we can enhance it using maybe a CNN or LSTM, or use transfer learning to enrich the model's performance. And right now, the quality of the data set is lacking certain diversity. Hence, we will work to produce a high quality data set so that we can use it for enhancing any model's performance. Here are the references used, and thank you very much.